Today we will be talking about humidity, and then we will start with the pressure sensors. So this will be a lecture for today and for next week, and next week we will complete some pressure sensors. So let me start with sensors for humidity. I will show you some principles, how it works, and I will also show you how can you use the sensors, and how can you connect the sensors, and what properties they have. First, let's define what is humidity. We will use two definitions of humidity. One will be absolute humidity and the other will be relative humidity. So the absolute humidity is the contents of water vapors in some specific volume. So here we are looking, for example, how many kilograms or grams of the water we have in some specific volumes, such as 1 cube meter. We will not see any sensors for absolute humidity because they are quite complicated, and most commonly used sensors are measuring relative humidity, and then by using tables and equations you can recalculate actually to the absolute humidity. So all the sensors that I will show you today will be for relative humidity, and relative humidity is the content of water vapor, but it is compared to saturated air. So we compare what we currently have, how much water vapor we have in some volume, to the maximum possible volume. So this means that relative humidity will be some number between 0 and 100%. We will see that humidity depends also on temperature, and if we will have some changes in the temperature, the relative humidity will change as well. You know this from nature. When in the morning outside you see water droplets that have condensed on some trees and grass, for example, and this is due to the fact that during the night it was cold, the temperature dropped, and then the relative humidity increased up to 100%, and then the air was not able to hold the water anymore. So we'll see those sensors quite often have temperature sensors as well. So especially the digital humidity sensors, and they have a thermometer inside, and you can read the humidity and temperature at the same instant, so that you can relate those two variables together. We will also see that some of the hygrometers they work with the dew point, and the dew point is the temperature and pressure at which the gas begins to condensate into a liquid, and that will be the very first humidity sensor that I will show you. So let's take a look on this chilled mirror hygrometer, as it's called. Now this hygrometer does not measure directly the humidity, but it measures the effects of the humidity. So how does it work? The principle is shown here on this picture. This is a mirror, or it's a window, and we know that when we have a cold surface, that this cold surface will cool the air down, and hence the humidity will increase. And when the relative humidity is 100%, then the water in the air starts to condensate here on this surface. So this is the principle. In the real sensor, we have a mirror that is shown here, and we can change the temperature of this mirror. So we can heat the mirror and we can cool it down. The way it's done is typically with a Peltier element, so Peltier cooler, or it could be done with two separate systems. Anyway, here this element can heat and cool down. And we are looking for the effects of the dew on the surface of the mirror. So we have a light source. It's a typically an LED, and this light source is projecting a light beam on the surface here on the mirror, and we measure how much is reflected, and this is measured with a light detector. Since we are not looking for an absolute value of the reflection, but we want to compare if the dew is on the mirror or if the dew is not on the mirror, then we do not measure directly the intensity of the reflected beam, but we compare it with a beam that is going directly from a light source to the detector. So here is a reference beam with the same LED with the same detector, and this reference beam goes directly. So if there is no dew on the mirror, then basically this reference beam and the measuring beam will have about the same intensity. But say as soon as we will start to get dew here on the mirror surface, the intensity will drop because the radiation will be absorbed, and here we will have a drop in the amplitude. So we compare the reference beam with the measuring beam here with those two detectors. The difference is then amplified in an amplifier, which we see here, and it all goes to a control block, and this control block could be, for example, a microcontroller, and this microcontroller measures the amplitude from the amplifier, so this difference of the signals. It measures the temperature, and it is able to control the power that we supply to the heater and cooler. So this chilled mirror hygrometer works in cycles. It typically looks like this. It does not have to be just an optical detection, but we can detect also changes of capacity, which you can see here. So here let's start here on this picture on the bottom right. This is the surface as we will see it without the dew on the surface. So here there are no water droplets, and as the temperature of the surface is dropping, we see that we have more and more water droplets on the surface. So this can be detected optically, or as in this case it is detected as capacitive changes. So here those wires, this grid, this forms a capacitor, and we are looking for capacitive changes. So it can look like this when you look under the microscope on it. So again, this array forms the electrodes. It can be made on a chip, so in the cross-section view it may look like this. If it's on a silicon chip, so this is the silicon backing material. Here we see the heater to increase the temperature of the mirror. The cooler in this case is an external one, so here we see that here we would have an additional cooler because we need to drop the temperature down in the cycle as well. And here we see that those electrodes here, they call it impedance detector, and on those electrodes we are able to detect the water droplets. So then the real device looks like this. We see this white rectangle, this is the cooler, this is the Peltier element, and this aluminum piece, it's a heat sink, and that allows us to remove the heat from the Peltier element into the ambient air. And here this would be the chip as we see here, and here where we actually measure the humidity. So now how does it work? Let's show a graph to show the principle. So this works in cycles. So we first need to cool down the surface mirror until we see the water droplets. So if I plot a chart where here we will have time and here we will have temperature, we usually start at a temperature that is slightly above the ambient temperature, and this is measured by the temperature sensor. So we first apply some power to heater, and this will heat it up slightly above the ambient temperature. So we will be somewhere like this. Then we will start cooling down this surface, and the temperature will drop. It will be some transient response. I will plot it as a transient response of a first order system, although it would most likely be a high order system. But just due to simplicity, let's make it like this. So the temperature now is dropping. Let's say the dew point, the dew temperature, will be somewhere here. So when I'm below this temperature, then here in this area I will start to get the water droplets on the surface. So here I'm still cooling down the mirror, and at this moment there will be water droplets that will start to appear on the surface, and this gets detected by the beam. So we will cool it down slightly below the dew point temperature. We can detect at which temperature this started to happen. And slightly below means few centigrades, let's say 5 centigrades approximately. And then we need to heat it up again. So then we'll increase the temperature like this. Again, it will be a transient response. And here, as we heat the mirror up, the water droplets will evaporate and we'll get again a clean mirror. So we will be able to detect it again. And we will heat it up slightly above the dew point temperature, which will be something like 5, maybe 10 centigrades above it. And this cycle repeats over and over. So again, here I will cool it down, I will measure the dew point temperature, I will heat it up, and so forth. So this cycle repeats itself. Now the period of those measurements that we have over there is typically in the order of around 10 to 20 seconds. It can be longer, it can be a little bit shorter, but it cannot be much shorter because here we have some thermal inertia. So it's in the order of few tenths of seconds. So this is not a continuous measurement, but in most cases you don't need to have a continuous reading of humidity. It's completely sufficient that you have like one sample every 20 seconds, maybe 30 seconds. So in this case it's completely sufficient. The chilled mirror hygrometer is a very precise device. It's actually one of the most accurate hygrometers. But as we see, it's a quite complicated device, so it will be also quite expensive. So here we get a precise reading, but we have a quite high price of the device. Another advantage of this hygrometer is that it does not add any additional humidity. Here we have the gas flow, that's where we want to measure the humidity. Here we are obviously changing the relative humidity, but we're not adding anything, so we're not increasing the absolute humidity that we actually have in the measured gas. So it's suitable for small spaces, for small boxes, small rooms where you want to measure the humidity, but you don't want to change it with your measurements. This will not be the case of one of the other sensors that we will see in a minute. So now let's take a look on the device itself. So here are 3 examples how this device may look like. In both cases we need to have some chamber where we actually have the sample. So in this case it's here, and in this case we will have the mirror itself. So the mirror here is in this cavity. We can open actually this to facilitate the cleaning of the system, and here we see a large heatsink because we need to remove and add quite a lot of heat in order to make it work. So it is quite power hungry as well, especially if you use the Peltier elements. Then the current may be few amperes with few volts. So let's say 10-20 watts of electrical power may be required to operate the Peltier element. We see the internal construction on this picture. Here we see the light source and detector. So in this case it is in the bottom, in here. Here we have the inlet and outlet ports for the sample. So we blow the gas, the air through this chamber with a fan, for example. And here is the mirror, and all this will be heated and cooled. And here we see some optic lines that will focus the light properly on the detector and from the light source. So here in this chamber we will actually measure the relative humidity. Those chilled mirror hygrometers, as I've already said, are very accurate, but are quite expensive. The price of this may be a few thousand euros if you are looking for something very accurate ones. I will later show you some comparison of accuracies and properties of the other sensors when we complete this chapter about hygrometers. So that's the very first one type of hygrometer. Now let's take a look on something else. It will be a hygrometer as well, but this hygrometer will not measure directly the humidity, but it will measure temperatures. And from temperatures we will be able to measure the humidity. So how does it work? There is a quite nice video here on this link, so I recommend you to take a look on it. Here we will take a look on the principle, and the principle is the following. When we take two thermometers, one thermometer will measure the temperature of the air, but we are looking for humidity, so this is an airflow, and this measures directly the temperature of this air. We will call it a dry thermometer. The second thermometer will be wrapped with some cloth like this, and this cloth is soaked with water. So we can imagine that like it is submerged in a tank, and this cloth is soaking water. We will call this the wet thermometer because here it's wet with this water. It's typically distilled water. And now what happens? Here we will have the same airflow. This airflow was typically provided with a fan. So later on next slide, when you will see the real photographs of this device, we'll see a fan that provides this airflow. Now as this air is flowing, it evaporates this water. So there is water constantly evaporating from this cloth. And when there is evaporation, we will remove the heat. So therefore the temperature on the wet thermometer will be different from the dry thermometer. It will be smaller. And if we measure the temperature difference and the temperature of the dry thermometer, we can find what is the actual humidity of the airflow. We will see later, it's called a psychrometric chart or psychrometric equation, and this equation relates us exactly the dry temperature and the temperature difference with humidity. So by measuring simply two temperatures in this setup, we can get what is the actual relative humidity of my air. Let's take a look on this psychrometric chart. So let's say that my dry bulb temperature, it's also called dry bulb and wet bulb, so that my dry bulb temperature would be, for example, 25. So here we have the temperature from the dry thermometer, so that's the one without the cloth. And the wet bulb temperature, it's here shown in blue. That is the temperature of the saturated air when we had relative humidity of 100%. And this is what we read from the wet thermometer. In some charts, on some tables, you will find directly the wet bulb temperature. In some tables, you may find the temperature difference. In this example, we have the wet bulb temperature directly. So let's say we would have 25 on the dry bulb. So here I'm looking for this line, and we would have let's say 20 centigrades on the wet bulb temperature here. So here we are looking for this intersection, and here we see that those red curves give us relative humidity. So in my example, the relative humidity would be something like 60%. It is accurate within few percent. So it's possible to build a very simple hygrometer like this. Just you need to take two temperature sensors and arrange them in this setup. The temperature sensors, they can be anything. So this could be a glass thermometer, for example, but it could be also some precision resistive temperature detector. So it could be an RTD, a PT100, for example. So there are many available devices like this on the market. Some have thermistors, for example. Some may have PT100s, but it's mostly thermistors because of the price, and we don't need such a high level of accuracy for the temperature. If we calibrate the sensors properly, here it may be sufficient to have resolution of, let's say, 0.5 centigrades approximately. This is not a very precision device. You may measure with it within a few percent of relative humidity. So let's say plus minus 3, plus minus 5, which is usually sufficient. Here are a few examples how this psychrometer works. So here on this animation we actually see the Sling psychrometer, as it's also called. Here we see that they are using two thermometers. The one here, this is the tank with water, with this distilled water, and now as you sling it, then you actually provide the airflow, and we see that here this is the dry bulb, this is the higher temperature, and this is the wet bulb, it has the lower temperature. And we may have a scale here, and we may read directly the humidity, or we may have a table on the back side, and we can calculate the humidity ourselves. So the real thing looks like this. This part you hold in your hand, you turn it, this part is slinging. Here we see one thermometer, another thermometer, and then on the scale and the table we may read what is the actual humidity. Similar examples are over here. Basically the same principle, just here we have the different kind of handle and here we see the two thermometers. Here this is the wet bulb, here we see the tank that we can soak with water, and this is the dry bulb. Here note those holes. Those holes provide you an opening to give you the correct airflow around the thermometers. Here we can see that this is the dry bulb, here we have the higher temperature, and here we have a lower temperature. So this is a manually operated device. On the picture here on the very right we see something that's a little bit more automated. Again, two thermometers, and here on top there is a fan. So we turn on the fan, it provides airflow around the thermometers. This will be the wet bulb, this will be the dry bulb. So here on the wet bulb there will be the cloth that you have to manually soak in before you start the operation. But it can be done also automatically. You can have an electric fan here. Those thermometers can be replaced with thermistors, for example, and then you can measure automatically the humidity with this kind of device. Now we can see from the principle here that we are actually adding some humidity here in this system, because here we need to have some tank, we need to maintain it regularly. So this is more supposed to work as a one-time device where we need to measure the humidity somewhere, and it's not meant to operate as a continuous device. So it's not like a kind of industrial sensor, but it's a sensor that you use in air conditioning applications. You go around the room, around the building, you measure the humidities, and you can adjust the air conditioning to give you a good temperature and humidity, for example. So this adds the humidity to the measured air. It is not very suitable for small enclosed spaces, because very soon this would change the relative humidity of your device. So for example, if you have like a small box, small room, then soon it will increase the humidity above what you actually measure. Okay, so that's the second hygrometer. Again, we'll see it in the comparison at the very end. And now let's take a look on the last example. This will be an industrial grade sensor, and it will provide us an electrical output signal. So how does it work? It is also called a dry electrolyte hygrometer. The electrolyte is aluminum oxide, so this is Al2O3, and this is forming an electrolyte here. Here we have this material. We are looking for the changes that will happen in this dry electrolyte with humidity. And we can either measure changes of capacity or electrical resistance, or both. So this will work as a capacitor. Here we will have one electrode, and here we'll have a second electrode. The one electrode that is here on the bottom is typically made directly from aluminium. It's a thin film electrode, and this is a solid electrode, so there are no holes in the electrode. The electrode that we have on the top needs to allow the humidity to enter and to exit from the electrolyte. So this needs to be a porous electrode, and it's typically made from gold. So here on the bottom pictures we see those two electrodes. Here, this one on the left, this is the aluminum electrode, so we can see there are no holes, no openings. We don't need any holes in here. And here, this is the gold electrode, that's the one on the top. We can see this typical honeycomb structure, and we can assume that the humidity, the water vapor, will be able to enter through those openings into the electrolyte. So when there will be some humidity that we add, we will actually change the resistance and capacity of this. And then when we place the sensor in an environment that is dry, then the humidity will evaporate from the electrolyte, and again will be detected as a change of resistance and capacity. So let's take a look on how this looks like. So we'll first focus on the chart here on the left. Here we can see that the curve A, this is actually the capacity of the device, and curve B, this is the resistance that we have there. And we can see that both are changing somehow with relative humidity. So here on the x-axis we have the relative humidity from 0 to 100%. We can see that in both cases it is a nonlinear function, and in some ranges we may use capacitive detection, in some ranges we may use resistive detection. So for example, here if we look on the capacity change, we can see that this is a fairly good response. Here we have quite high sensitivity. Here when we change the relative humidity, there is a significant change of capacity. Well, significant, this is in nanofarad, so it's not that big, but it's possible to measure it. But here, let's say above 50% and more, we can see that this is a flat response. So in this region we will have no sensitivity at all when we detect capacity directly. On the other hand, if we look on the resistance that we have over there on the curve B, we can see that above 50% we have a suitable, let's say, slope, and we can measure the resistance changes here. So if we want to build a sensor that is operating from 0 to 100% relative humidity, we need to combine those two principles. So here, when a capacity is available, here I can measure up to some around 50%. Then I need to switch to resistive detection, or I could use the resistive detection from somewhere around here, from somewhere around 10, maybe 15%, and then follow this curve to the very end. We can see here that the resistive detection here has also a flat response like this, so it will not be able to detect very small humidities. However, this is done automatically in the hygrometer, so you will just get the output signal, and the output signal is typically linearized. It can be a voltage, it can be a number, so we don't need to care about those responses, but it's a good idea to know what is actually happening in the sensor. Now, how about the response time? It is clear that we are here relying on the changes based on the absorption of the humidity in the material. So it will take some time before the sensor can actually react. And we can plot this as a transient response. You can see an example of the transient response over there. So this is the time in seconds, this is the change of relative humidity, and the transient response is made like a step change. So for example, here this would be a step when we are increasing humidity from somewhere around 10 to, let's say, 65, maybe 68%, like this. So we take the sensor, we place it in one environment, in one box where we have this humidity, then we move it to a different environment where we have this humidity, a second box where we actually have some water vapor, and we are looking for the reaction on the sensor like this. So this is the transient response. You can see that this is a first order transient response, and we can simply measure the time constant. The time constant is done as a tangent here, so like this, and this will be my time constant of the sensor, so it will be somewhere around 3 seconds. We can do the same also when we are doing desorption, so we start in an environment where we have almost 100% relative humidity, and then we move it to a different environment, so my step change will be like that, and again I can make a tangent like this, and we can see that here the time constant is longer, so here it's about 5 seconds. So this is typical for those humidity sensors. They have a smaller time constant when you are increasing humidity, and then it has a longer time constant when you are decreasing humidity. It's not that significant, but in both cases it's in the order of few seconds. So it can be 5 seconds, it can be 8 seconds, for example. Here is an example of such humidity sensors. So this is the sensor itself, so this is the opening where you allow the humidity to actually enter into the chip. In the chip you have electronic circuits that evaluate the changes of capacity and resistance, and they produce an electric signal. Some humidity sensors have an analog output, so then you can have voltage or current that is a function of the humidity. This particular sensor has a digital output, so with the digital bus, in this case it's called I2C bus. In this case you can read directly the humidity as a number, and it also has a temperature sensor, so you can read the temperatures as well directly. In most applications you need to have the temperature anyway, so you can use a combined sensor like this. So this I2C bus, it's a 2-wire bus. One wire is data, one wire is clock, and the 2 other pins are the power supply voltage. So you can see that here we have 4 pins, and this is the digital sensor. Now, so that's the chip itself. Then When combined into an industrial system, it may look like this. So the sensor itself is placed here under this cover, under this protection. It's like a pipe, and it's protecting the sensor from mechanical damage. It needs to have some openings to allow the gas to enter inside. And here this unit is simply reading the data from such kind of sensor. Here it shows you the humidity, no, this is temperature in both cases, but it's a hygrometer sensor, and it also has an output signal. So here on this cable we'll have the data about the humidity reading. It can be operated also as a handheld instrument, so like this. So here you see this slot. This is actually the opening that allows the air to enter into the sensor. The sensor will be somewhere around this place. You hold this in your hand, you go around the room, you put it in the box where you want to measure the humidity, and then on the display you see what is the actual humidity in the environment. So this sensor has a signal as an output. It's very common to have those sensors. If you have at home some hygrometer with a display, then it's very likely that it has this kind of sensor. But we'll skip this hair hygrometer, and I will just go to the calibration. How to calibrate the hygrometer. The calibration needs to be done in an environment where you have a constant humidity, and this can be achieved with a solution of a saturated salt. So you can take a small box like this. This is a cap actually from some plastic bottle. You can put the salt in it, and then you add this water so that the salt is soaked with the water. It's like forming like a paste. It's a saturated solution. And you take your hygrometer that you want to calibrate, and you place it in a plastic bag or in a box where you can actually enclose it. In a few hours what will happen is that this will have a constant humidity, and you can read what is the reading from your hygrometer, and then you can calibrate it. You can say, okay, now I know that the humidity in this box should be 75 and it's reading 76, so I need to adjust it. You can calibrate it with different salts. So for example, here you see some selected materials and the humidities. And the reason why this works very well is that this gives you quite good relative humidity that is almost constant with temperature. So although here the temperature may change, the humidity in many cases is almost constant. Well, I say in many cases, but here we have plus minus 10%, plus minus 15. But we can be fairly sure that, for example, if we have 25, then if it's in the room, then it will move maybe between 23 to 26 centigrades and so on. So here we can see that, for example, if we take sodium chloride, there's nothing else than ordinary salt. Here we have approximately 75%. And here when we use the temperature, let's say from 25 to 20 and 30 centigrades, we have 75%. Here we have a little bit less, but also with a very good accuracy. The hygrometers that we can calibrate like this are typically looking like this, as say normal household hygrometers, and they measure with an accuracy of plus minus 5% anyway. I forgot to tell you the accuracy for this kind of hygrometer is typically a few percent. So a chip like this, even the most expensive ones that you can get, they will measure within, let's say, plus minus 2% approximately. And the normal ones that you can get, the cheap ones, that will be something like plus minus 5, plus minus 8%. So it doesn't make sense to calibrate the hygrometer within 0.1% because the sensor is not able to measure it anyway. Okay, So let's take a look at the comparison of the different sensing technologies. Now, out of this table, we have discussed only 3 of them. We have basically discussed just this one, that's the chilled mirror hygrometer. We have discussed this psychrometer, and then we have discussed this group of capacitive sensor. We have not discussed the other ones, but just those 3 groups. So in what range can they measure, and what do they measure? So we've seen that the chilled mirror hygrometer measures the dew point temperature. The psychrometer measures the wet and dry bulb temperatures. And here this measures directly humidity and temperature eventually. In what range can it work? Well, this can work. In this case, they give the reading for temperature, so we can see the temperature reading, but humidity reading is from 0 to 100%. This cannot measure very dry air, so here we typically operate it between 20 and 100%, and this can measure between 100 and 0% as well. This actually depends on the type of the sensor that you have. Some hygrometers, based on this principle, they can work, for example, from 0 to 80% RH, or from 10 to 80 or 90%, and only some of them can really operate from 0 to 100%. Especially the more expensive ones can operate in this range. How about accuracy? Here we are somewhere between, let's say, 1 to 5%, but 1% here for this kind of sensor, that's very accurate. Typically on the market you can find sensors for relative humidity based on this principle that start from somewhere like 1.8%. This is a little bit less accurate. Here they say about 3 to 4%. Anyway, it's a little bit less accurate than this kind of sensor. And here they say high, but this is actually the highest. It could be something like 1, maybe 2% of accuracy. How about the response time? Here the response time can be few seconds. So this is based on the sensor construction. The sensors we are using in the labs are about 8 seconds. So here they say from 4 to 10, here from 15 to 60 seconds. So few seconds. Here we can see that the response time is actually much longer. So here the response time is in the order of few minutes. So something like 2 minutes, 3 minutes, that's the normal response time that you can expect from this psychrometer. And in the chilled mirror hygrometer, it's typically some 10 seconds, 20 seconds, something in this order. So it's somewhere between the psychrometer, which is here, few minutes, and few seconds, as we can see over there. Okay, so that's all about humidity sensors. And now we will discuss pressure sensors. We'll see that there is a relation between pressure and humidity, and today we'll learn some principles how to actually measure the pressure. First, let's define pressure, and I will show you 2 definitions, and both definitions will be used in pressure sensing. The first definition is that we measure the force that is acting on a given area. So this could be, for example, a piston. We know the area, we can measure the force with the force sensor, and then we can calculate what is the pressure. The second definition, and we will see it also used in pressure sensors, is using hydrostatic pressure. So let's say we have a tank. We have a liquid with some density rho here in the tank, and we have some height of the liquid. And if we measure the pressure at the bottom, we can calculate what is the liquid level actually. So here you see such an equation. It's density times gravitational acceleration times h. So for example, if we want to measure some pressure of some gas or some liquid, we can just translate this to a height of some liquid. We'll see that the very first principle that will show you what exactly this will use exactly this approach. Now let's take a look a little bit on the units of pressure. Now the SI unit of pressure is Pascal, but in pressure sensing it is very common to use also different units. So for example, here we can see that 1 bar corresponds to 10 to the power of 5 in pascals. So it's quite useful to have actually some idea about the size of those units to have an estimate how much that is. Now this table, this is only a selection. There are many other units that are actually used, and you may still find them on pressure gauges. So this is 1 millimeter of water column. So this is using the hydrostatic definition, and this corresponds to about 9.8 pascals. You will actually be also able to find 1 millimeter of mercury, which is called 1 torr, and this is 133 pascals approximately. And here this is the physical atmosphere, is defined as this value in pascals. And here we have 1 psi, that's 1 pound per square inch, and here this is the value. So it's a good idea to remember those values approximately, so that if you see some pressure gauge with the values written in different units in pascals, then you have an idea how much that actually is. Okay, let's take a look on what types of pressure we can actually measure. And based on this, we may have different principles in pressure gauges. The first thing is that we can directly measure the absolute pressure. Now the absolute pressure is defined versus a vacuum, and we will see specific pressure gauges that are able to measure the absolute pressure. So this measures from zero pressure. More common, you will find differential pressure gauges, and in this kind of appliance we measure from some reference pressure, and typically this reference pressure is the barometric pressure. So we are looking for overpressure or underpressure as compared to the actual atmospheric pressure. And we'll again see some examples of those differential pressure gauges. So let's take a look first on the calibration instruments. So those calibration instruments will be used as primary pressure standards, and this means that the sensor is based on the definition that we have just seen. So it measures the force on the area, or it measures the hydrostatic pressure. So this is a calibration instrument. It uses the definition, and in this case we can use it to calibrate all other instruments. So all instruments that we will see today will be in this group. They will be calibration instruments. But we will see next week that those instruments are not industrial grade instruments. They are either very expensive or they are very sensitive to damage, so they will not be used directly in industrial applications. So in industrial applications, in most cases, we do not use those calibration instruments. Those calibration instruments are used in labs or during production when you want to calibrate the other instrument. But then the other industrial instruments will use different principles, because the other principles will be more robust, will be more reliable, will be less expensive. So let's take a look on two ways how we can actually measure and calibrate the pressure that we want. The first example that we see now on screen will use the hydrostatic pressure. It's called a dipping bell pressure standard. Now this instrument can give you very accurate readings in very small pressure ranges. It typically ranges within few kilopascals only. So it's for small pressures. Now how is this working? Now we have a tank like this, and in this tank we have a liquid. It can be water, for example. So this is the liquid level. Now in the tank we have a bell that is dipped into the tank. It's inverted, so here the bell is facing downwards. And here is the pressure that we actually want to measure. So I want to measure the value of pressure P. Now the pressure P is bigger than the atmospheric pressure. So here it's bigger than the pressure around in the ambient environment. Now what will happen is that here we connect the measured pressure, and here we will measure what effect does it have on the bell. Now we will compare the two forces that are acting on the bell. So one will be the force that is actually created by the pressure. This will be called the internal force, Fi, and we know the area here, we know the dimensions of the bell. So this is simply pressure times the area. And the second force will be the force acting on the bell by gravity. So this will be the external force. So this will be the force that is facing down. And it will be a function of the geometry here, so on the shape, on the dimensions, on the volume, on the material. So this is shown here in this equation. So here we have the gravitational force, here we have the dimensions, and here we have some length and density of the liquid as well. So this is the external force. Now in steady state, those two forces will be in equilibrium. So here we will have this equation. Now also, if this pressure is higher than the ambient pressure, the bell will move up from the initial position. The initial position without pressure was somewhere here, and now we have some distance at L that we actually can measure on the scale. So on this scale we can actually read the length. How far is it pushed away outside from the liquid? So now we can calculate the pressure that we want is the external force divided by the area, and basically we can see that all this is a constant value. So area is constant, density is constant if temperature is not changing, gravitational acceleration is constant as well. So this is a constant times length, and length that's what we actually read on the scale. So it's a linear response, and we can see the linear response here. Here we have the pressure that we measure, and here is the length that we read from the scale. So this is this kind of linear response in this region. Now what will happen if we are at the end of the scale? We can increase the range, we can extend it by adding additional weights. So we can add a weight here on top of the bell. This will push it back into the liquid, and we can go back to the beginning of the scale, and we can increase the pressure again and over and over. Of course this works only until you still have some liquid here under the bell. If the gas starts to escape from under the bell, it does not work anymore. So this is the limitation. How far can we actually extend the range? Now here is how the device looks like, and its parameters. So it is operating typically in a small range of pressures, somewhere from 0 to 1, eventually 3 kilopascals. So this is for small pressures, but it's a very accurate device. You can see the resolution 0.01 pascals. Those numbers are actually for the device here shown in the picture. So it's a very accurate calibration instrument that can be used for small pressures. Okay, So that's the first calibration standard. Now let's take a look on the second one, which will use the piston approach. This device is called a deadweight tester. Here is a piston. We know what is the area of the piston, A, and we want to measure the pressure that is created by this fluid. So this fluid can be oil, typically can be water, can be air, for example, but typically it's oil. And here this fluid is creating a force that is trying to push the piston out. So this is the force F2. And against this force we need to have another force F1 that will be gravity. So we need to know the weight of the piston, and we eventually can add some weights on top of it. And when this is in equilibrium, we can calculate what is the actual pressure of this fluid. So we're again looking for the balance of forces between F1 and F2. And then we can simply calculate that the measured pressure is force over the piston area. Now this looks like a very simple approach, but it actually is not that simple. We need to remove many influences that we have in the setup. We need to remove, for example, friction. So here there will be friction in the piston and in the cylinder. So we need to remove this. We need to remove the influence of temperature, and so on and so on. So although the principle itself it's quite simple, the device is not, and the device will be quite expensive. Here is the inside of this deadweight tester. It's typically used to verify and calibrate other pressure gauges. So for example, here you have a test gauge that you want to test. So it can be something like this. You want to verify if it's reading properly on some given positions of the scale. So you connect through a connector this gauge to the deadweight tester. Then here this is the actual piston in the deadweight tester. This is the cylinder and this is the piston. So this is where we measure the force actually. And here we have the weights. You can see the weights are shown here on this picture on this side. So this is the weight, and here we have the cylinder. And here typically we have a pump. It can be manually operated or it can be automatically operated. And with this handle we can actually pump the liquid inside and we can create some pressure. And here on this deadweight tester we have a scale. We pump the oil inside, we adjust the position of the scale to the correct position. This means that we have the correct pressure, and then we read if this gauge under test is reading properly. So this is a device that's used for calibration of all other instruments. Let's take a look on the ranges. Here the ranges are for higher pressures. So it starts typically from something like 100 kilopascals. It can go up to 200 megapascals. So this is a device for very high pressures. It's not operating for small pressures properly. Here we can see that it's also a very accurate device, so within 0.01, 0.02% approximately. Again, those numbers are for the instrument that you can see here on the screen. You can see here that this is the weight. There will be a valve over there that in here where you connect the instrument under test, and then you turn this lever to adjust actually the pressure that you have inside. In this case you have the pump for priming, so with this pump you manually operate this, and you can change the pressure. Now during operation those disc needs to spin, so it's rotating. You made it rotate manually, And the reason for this is that the rotation will allow you to decrease friction in the piston. So here in this piston the pressure, the friction will be decreased, and you have less friction in the system. Now you can see a price estimate here. So this is a quite expensive instrument. It's like a small car maybe. So it's like $8,000, even more, for those kinds of instruments. So those are very expensive devices. Okay, let's take a look on some other calibration instruments. I'm sure you have seen this device somewhere in some other classes, like fluid mechanics probably. It's a U-tube manometer. It is also based on the hydrostatic principle. So we are looking for the hydrostatic pressure, and this allows us to measure our pressure. This can be operated as a differential pressure gauge. So we can measure difference between P1 and P2. Now in this picture, it's in my example, P1 is actually bigger than P2, but it can actually measure also in reverse without any problem. So this is a U-tube. Here, this is a transparent tube made of plexiglass, made of glass, whatever is transparent. And here, if P1 is larger than P2, we will see something like this. So there will be a scale on both arms here, in here, and here there will be a scale as well. And we are looking for the height difference. So it's obvious that if P1 would be equal to P2, then here this height difference will be 0. If P1 is larger, then we'll have some height difference. And we can simply calculate the pressure difference as by the H, that is the height difference, times gravitational force, times the difference in densities of the fluids. So here this is the density of my gas, typically air, and this would be my density of my liquid, whatever I use. So if it's water, it's approximately 1000. If I use alcohol, it's approximately this. If I use mercury, it's approximately this number. It is changing with temperature, so those densities are valid for 25 centigrade. So it's a simple device. It typically does not have any electrical output, so it's manually operated. The operator reads the height difference and you can calculate the scale. It's quite useful because it's very simple to build such a device. You just take a transparent hose and you have a pressure gauge, a very simple pressure gauge. How to read it correctly? We need to know what liquid do we actually have inside. So if it's water, then it will form this shape, and we are reading the bottom edge here. The same for alcohol as well. In many cases, those instruments, they use mercury because mercury has a larger density, and this allows us then to measure larger pressures. So you see it's about 13 times higher density, so we can measure about 13 times larger pressures. With water, if you remember the table with units, 1 millimeter of water was about 10 pascals. So with water, if we have the height of about 1 meter, we can actually measure just about 10 kilopascals. But with mercury, we can measure a lot more, 13 times more approximately. So although mercury is toxic, then it's quite common to see mercury in those pressure gauges. So for mercury, we need to read it like this. Here, the mercury has a different surface tension, so it will form this shape, and we are reading the top of it. You also need to avoid the parallax error, so it means that you need to look like this in a perpendicular direction to the scale. So like this you are reading it correctly, like this you will read a higher pressure, like this you will read a lower pressure. So you need to move your eyes to have a correct position. Okay, Few examples. So YouTube manometer can look like this. You see a simple transparent tube. Here is a scale in millimeters. Here we see that this is water or alcohol because of this surface tension that we see here on the shape, and we can simply calculate what is the pressure that we can measure on this device. You can see the same here. Again, this looks like it's either alcohol or colored water. The colors is added to simplify the reading from the scale. So it can look like this. It can have many shapes that you can actually find. Well, this is again a handheld operated instrument. It's typically not an industrial grade instrument. Okay, now let's take a look on the barometer. Again, this will be a handheld instrument that you will find in labs, that you will find anywhere where you need to read the pressure. So here it's operating on exactly the same principle. We are looking for the hydrostatic pressure. Now the difference is that here we have replaced the pipe with a tank. So here we have a tank with the liquid, and here we have the pipe. If here we have pressure P1 and pressure P2 here, we can read the height difference. Now typically we can neglect this difference in the tank because compared to the volume that we have in the pipe, this is significantly larger. So the drop in liquid level here of H1 is typically very small. It is there, but compared to H2 is negligible. This device can operate as a relative sensor, or it can work also as an absolute sensor, as a barometer. So if this opening here for P1 is open, I can connect one pipe, one probe here, P1, on this port, and one probe here, and I can use it as a differential gauge. If I close this, then I will use just this port, and then it will be able to measure the absolute pressure. We need again to read just the height here, so we need the scale, so we will read from the scale in millimeters, and then by using this formula, which is again H times G times rho, then we can get the density and the pressure. Typically this is air and this is water or mercury. So again, there is a really large difference between the densities. So if this is air, it's something about 1, and if this is water, it's something about 1000 kilograms per cube meter. So in the equation we can really neglect this rho 1 if it's air and if this is water or mercury. So then it's just the density of the liquid times h times gravitational acceleration. Now this operates in approximately the same ranges as the YouTube manometer. So about 10 kilopascals for water, because then this pipe will be very long and it will be very inconvenient to read it and to move the instrument around. So this length is typically about 1 meter at max. Now this is how it looks like. So typically here this is the transparent tube. The well is from the back side or inside of the instrument. Here you have one port for the pressure gauge for the connection like a hose, and here you can see that this is either colored water or colored alcohol. You can have multiple in one device, so you can read multiple pressures whatever you require. Now the accuracy is typically very high, below 1%. We can read quite accurately this distance, so it's a quite accurate instrument. On the other hand, it has a typically smaller range compared to the mercury types. This is for water. For water, the maximum practical size is about 3 meters. Otherwise, you need leather, and therefore we are limited to somewhere like 3 kilopascals approximately. If you have a small device like a 1 meter length only, this will be like 1 kilopascal only. So this is a device used for smaller pressures. On the other hand, if we modify this pressure gauge, we can increase the sensitivity, and we can decrease a little bit the range. So we decrease the range, but we increase the sensitivity. And the way this works is that we are actually inclining the tube. So here you see such an example. This is a standard well-type manometer, but in this case the tube has been inclined. It's operating on exactly the same principle, but here this angle alpha now is something. It's not 90 degrees as it was before. And we again read the height difference. We are looking for some value from the scale. So it's operated in exactly the same fashion, but this is inclined. We can see in the equations here that now the pressure that we actually read depends on the sign of the angle alpha, and when this was 90 degrees, then this value was 1. So this is like an extension of the equation for the normal well-type manometer. Typically you don't need to read the angle directly. Typically you have some choice of the angles, and this gives you directly some coefficient that is written on the scale. So for example, you incline it a little bit and you will find that this increases the sensitivity 2 times, 4 times, 8 times. So you don't need to take care about the sine function, but you read directly what is this coefficient. Anyway, at the end it's very simple to operate again, because here we have some constant, and this constant we can see it's gravitational acceleration, it's the inclination, and then it's the density here. So it's again just a linear function, and the L here, sorry, this should not be L, but this, sorry, this should be L. This is like this. This is the length that we actually read from the scale. So this is the value of in millimeters that we read in here, times constant, which gives us a linear function. So like this we can actually increase the sensitivity. We will be able to measure smaller pressures with a higher accuracy. So it looks like this or like this. So there are many different versions. So here you can see it's just inclined tube. We will read on the scale, and that's it. Here again, scale, inclined tube, transparent from plexiglass, and we read the value in millimeters, so directly in pascals. We can also combine the two approaches together. So here you see such a device. So this is the inclined scale. We can see from 0 to 200 pascals it's inclined, so here we have good sensitivity. And then from 300 to 600 pascals, this is a vertical scale, and here we have a larger range. So this is a combined inclined tube with the vertical tube manometer. We can see approximately the ranges. Again, we are limited by the convenient length of the instrument. So this is about 1.5 kilopascals if it's for water. If we will use mercury, then we may use a larger range of the instrument. Anyway, the accuracy is about 1 pascal. It's limited by the resolution of the scale here. We are able to typically read within, let's say, 0.5 millimeters from a millimeter scale. So this is about this pressure that we can actually read. Again, this is not an industrial grade instrument. This is a lab instrument that you use for calibration of all other devices. Okay, so that's it for today. We will start with discussing the deformation manometers next week.